All right. So we are in the midst of chapter 8. So we've been talking a lot about Lewis structures. Yesterday we talked about formal charge calculations. And we talked about electronegativity and polarity, right? So we're talking about the chemical bonding between atoms, nonmetals. And the bonding between these nonmetals is covalent, right? So remind ourselves that when you have a metal bonded to a nonmetal, so for example, sodium, and let's use chlorine, so sodium chloride, that the big or the large differences in electronegativity, right? We said that some elements are highly electronegative, including the chlorine atom, 3.0, 3.1, depending on which table you use, much more electronegative than metals are. And so that very large difference in electronegativity results in the formation of not a covalent bond, not the sharing of electrons, but actually the ionization of the metal and the ionization of the nonmetals. So in fact, let me show you the Lewis structures for these, or Lewis dot symbols for each of these atoms. Okay, remember, chlorine is in group 7A, so it has 7 valence electrons. Sodium is in group 1A, so it has 1 valence electron. And what happens is the electronegativity of chlorine is so large that the electron from the sodium is actually captured by the chlorine atom. And so the sodium is ionized, it loses an electron. And so the result of that is that now we have an ion. So I'll put a little bracket around that, right? With no valence electrons, we've essentially removed the outermost electron. Now the sodium is positively charged. It's a cation. Likewise, because the chlorine has now accepted that 8th electron for it now, right? It had 7, now it has 8. It now is an ion, but it's a negatively charged ion. It's an anion, right? And so now what do we have? We have an ionic bond. And we can describe that process or explain that process from the perspective of electronegativity differences, right? Remember, the sodium ion was approximately 0.9 was the electronegativity. Chlorine was like around 3.0 or 3.1, a big enough difference that the chlorine atom actually removes the electron from the sodium, and we now have an ionic bond. When we have differences in electronegativities that are smaller than that, so for example, if we have a hydrogen and it's bonded to a fluorine atom, right? Well, let's actually start from scratch here. You've got the hydrogen atom, group 1A, 1 electron, 1 valence electron. You've got your fluorine, group 7A, 7 valence electrons, right? What happens? Well, what we've been talking about, the formation of a covalent bond occurs. Those 2 electrons pair up, spin down into an orbital, and now we have a covalent bond, the sharing of those 2 electrons. However, the large difference in electronegativity, right, 2.2, 4.0, results in a polar molecule, or polar bond in any case. And so what happens is you end up with a dipole. So you have a negative end on the more electronegative atom. Let me make these little circles bigger. A negative end on the fluorine atom, a positive end on the hydrogen atom, and you've got your electric dipole. Right, so this molecule will behave as though it has electrical properties. Okay, so we call that a polar bond, or sometimes it's called polar covalent. Okay, it's an electric dipole. And then we can have atoms that have almost no difference in electronegativity. So just to cut to the chase here, phosphorus is around 2.1 and hydrogen's around 2.1 or 2.2. Such a small difference in electronegativity that the sharing of those two electrons is pretty equal. So there is no electric dipole. So we would call this just a purely covalent bond, or just covalent, right? Sometimes people just call it covalent, but they would not call it a polar covalent bond because the difference in electronegativity is so small. Now what we're going to do today is we're going to look first at this phenomenon, which is called resonance. And resonance was first described back in the 1930s by Linus Pauling, consideration of Lewis structures and consideration of bond energies. And here's essentially the issue. If we take, I'm going to take the ion nitrate. Okay, so this is the nitrate ion. It's negatively charged, so it's an anion, right? What appears to be the case is that if we consider the energy required to break a chemical bond from nitrate. So let me show you this way. What I mean is by this. Suppose I took the nitrate and I put in some energy. And I put in enough energy to break a nitrogen-oxygen bond. What you get is this. Oops, sorry. Okay. You break off an oxygen atom, right? So the nitrate had 3 oxygens. Now it has 2. It's now a nitrite ion. So this is actually called nitrite. And an oxygen atom, right? And then you do the same thing. You take your nitrite ion and you put in some energy and you break another bond. Okay. And we start measuring how much energy it takes to break those chemical bonds. We're going to talk a little bit more about this when we get later in the chapter. But essentially, we're talking about breaking bonds. So here's what we would do. We would say, look, let's consider this nitrate ion. The nitrate ion has 3 oxygens. Okay. I'm not going to draw the full Lewis structure. I just want to point out that it has 3 oxygen atoms surrounding the nitrogen atom. Okay, it is an anion, so we'll write it as a charge here. The question is, how strong are these bonds? Like, how strong is the bond between the nitrogen and the oxygen on the left? How strong is the bond between the nitrogen and the oxygen on the right? And how strong is the bond between the nitrogen and the oxygen on the top? Are they the same? Are they different? And what we would do is we would say the following. It turns out that if you have a single bond between 2 atoms, that bond tends to have a certain strength. Now, it depends on which atoms are involved, but I'm going to just roughly say it's around 300 to 400 kilojoules per mole. And that's just an estimate, okay? It could be weaker than that. In fact, let's put it from 200 to 400. Okay, it's a range. But essentially, a single bond has some amount of energy in it. And it turns out that if you have a double bond between 2 atoms, in general, it has more energy because there's more electrons holding the atoms together, right? Instead of having 2 electrons, we got 4. You can almost think of the electrons as behaving kind of like a glue holding the atoms together, the nuclei. And what happens is, when you get up to 2 bonds, there's more energy, right? It's just a stronger bond, okay? 400 to 600 kilojoules per mole. That's the unit of energy that we're talking about holding these atoms together. And if you get a triple bond, it's even stronger. So maybe 600 to 800 kilojoules per mole. Okay, so there's a definite pattern in nature, which is the more electrons that are involved in bonding the atoms together, holding them together, the stronger that bond is going to be. So as we increase the number of bonds between 2 atoms, the general bonding gets stronger, okay? So that suggests then that if we have single bonds between the nitrogen and the oxygen atoms, they should be among the weakest of the bonds, right? They should be, this one's weaker and this one's stronger, right? So if we have single bonds, those should be the weakest bonds. On the other hand, suppose we had this. Suppose we had a double bond and a single bond, okay? So actually, let me draw it the same way I did before. I don't want to confuse people about that issue. Okay. So now notice this. And again, this is not a complete Lewis structure. It's just showing some bonding taking place. See how this one's a double bond? Right? That's a double bond there. And then the other ones are single, right? So single, single, double. What we would expect is that if the Lewis structure of this nitrate ion had a double bond and a couple of single bonds, one of those bonds should be stronger than the other two, right? That follows from this discussion here. The more bonds between two atoms, the stronger the bonds are. And, again, like suppose we had something like this. Suppose I said, look, there's actually two double bonds and a single bond. We would expect that two of those bonds would be pretty strong and one would be weaker. Except there's a problem with that Lewis structure, right? You can see immediately that's not a possible Lewis structure because there are 5 bonds to the nitrogen atom, 5 bonds, and there are 2 electrons per bond. That's 10 electrons. We've violated the octet rule. So that's no good. We know that wouldn't be possible, okay? So really we have a kind of choice. If we draw a Lewis structure where we have all single bonds, then all those bonds should have the same energy. If we draw a double bond and a couple of single bonds, then we should have different types of bonds in that molecule or in that ion, right? One of them would be stronger than the other two. And we can test that. We can test that by showing how much energy or measuring how much energy it takes to break these chemical bonds. So let's take a look at what happens. What I'm going to do is I'm going to take our nitrate ion and let's draw a Lewis structure for it. And let's see what we come up with. We're going to use the octet rule. And we also have formal charge that we could look at as well. But for right now, let's just consider the octet rule. When you see a formula where you have one atom and then a different element with more than one atom, we put the element that there's only one atom for in the center, right? And we call that a central atom. So the nitrogen goes in the center. And then we assume a single bond to all of the surrounding atoms, right? We talked about this last week. Then we do our electron bookkeeping, which is we count the number of valence electrons, subtract the number of electrons that we've just put in as bonds, and then we're going to have some left over, so we have to allocate those electrons around the surrounding atoms. And then if the central atom doesn't have 8, we form an extra bond to one of the surrounding atoms to get it up to 8, right? So that's essentially what we talked about last week. So nitrogen is in group 5A. So let's count up our valence electrons. Nitrogen is in group 5A, so it has 5 electrons. Oxygen is in group 6A, so it has 6, but there are 3 oxygens. And then you've got a negative charge, so you've got an extra electron. So that gives us 24, right? That's 24 valence electrons. We've already used 6 because we have 3 bonds, right? We assume there's at least 1 bond to each surrounding atom, so that's 6. So the remaining electrons would be 24 minus 6, which is 18. So then we distribute them in pairs around each oxygen atom, the surrounding atoms, until you run out of electrons. And you stop with 3 lone pairs, because when you do 3 lone pairs, that's 6 electrons. Add the other 2 for the bond, and that gives you 8. So it turns out that if you distribute 6 onto each surrounding atom, that gives you 18. Right? 6, 12, 18. Don't forget the brackets and the negative, right? So now we have our Lewis structure. The problem again is that this central atom only has 6. We have to form a bond. So now here's the issue of resonance and the issue of bond energies, bond enthalpies, bond strengths. we have 3 different atoms that we could use to form a second bond to nitrogen. We could take this one up here, we could take this one over here, or we could take this one over here. And so the question then is, which one is going to do it? And the answer is all 3 are going to do it. And that might seem crazy, but it turns out that's what actually happens. There is a second bond that is shared between all 3 oxygen atoms. Remember, the electron is a wave. So the electron has the ability to spread out not only across 2 atoms in the form of a covalent bond, but actually among multiple atoms, groups of atoms, through this phenomenon we call resonance. Okay? So this is the way we approach it from the perspective of Lewis structures. You identify every possible structure, every possible Lewis structure. So you have to be kind of imaginative, not that imaginative, but a little bit, and figure out what the possibilities are. There's 3 here. So one possibility, I'm going to number these with Roman numerals just so that we use a notation that books often use. 1, 2, 3. So the first one is the case where one of the lone pairs from this left oxygen is pushed over to form a second bond. That second bond will give nitrogen 8 electrons. The second possibility is this bottom oxygen uses one of its pairs to form a second bond. And the third possibility, I'll do that up here, is the third oxygen forms a second bond to the central nitrogen. So they're not all happening. We're imagining it as these are all the possibilities of what could happen, right? And so since there's only 3 oxygens, there's only 3 possibilities. If there were 4 surrounding oxygens, they could all do it. You'd have 4 possibilities. If there were only 2 oxygens, only 2 possibilities, right? So here's what would happen. In the case of 1, Roman numeral 1, we're going to have a double bond here. So I'm going to draw that structure here. And now this oxygen on the left only has 2 lone pairs. I'm going to actually move it over to the left because we need a lot of room for this. We're drawing 3 structures, right? So 1 structure there, 2, and then 3. Okay, so we're going to have a double bond here to the oxygen on the left with 2 lone pairs remaining on that oxygen. And then the oxygen at the bottom is going to stay the same as a single bond, oxygen on the right. Okay. Okay, remember, we need the bracket and then the negative. Okay, so there's one possibility, a double bond to the oxygen on the left. The second possibility would be a double bond to the oxygen below. So same idea, we just have the double bond down here. And I just want to make sure I show the lone pairs. Now, the term resonance is perhaps, I don't know, I would argue perhaps it's an unfortunate term. At least our connotation of what it means is, can mean, is a problem. So here's our third structure. And the reason I say that is that when we use the word resonate, sometimes it can be inferred that what we mean is something is resonating, meaning it's moving from one position to another, when that's not what really happens. So the term resonance is really that things kind of coalesce and they're in sync. There's a synchronization that occurs, right? So here's our 3 Lewis structures. These are Lewis structures. And what we've done is we've written all the possible Lewis structures that obey the octet rule for all 4 atoms and have the correct number of electrons, right? 24 electrons. Now what we claim, the phenomenon of resonance, is that the actual natural structure of the nitrate ion is the average of these three. Okay, so that's the key there. In resonance, the actual structure is the average of all Lewis structures. Now, there's a problem with that, which is how do you draw that? How do you draw the average? Well, you can't draw the average of electrons, right? Like I can't draw the average of 2 and 3. Like if I had 2 electrons and 3 electrons, the average of 2 and 3 is 1.5, 3 halves. You can't draw 3.5 electrons. Electrons are fundamental particles that cannot be divided up. So how do we do this? We can't really draw the average of this, but we can simulate to some extent. We can draw a little picture. If you take a look at what we have here, there's a double bond here, there's a double bond here, and there's a double bond there. In all of those cases, two of the bonds are single, right? So single, single, double. So if you said, what's the average of a double, a single, and a single, well, that would be 2 plus 1 plus 1, which is 4, divided by the number of structures, 3, 4/3. So that's 1 1/3. And it would be the same for all of them. So really, it's 1 1/3 bonds on average. 1 1/3 bonds is a little more than 1. So what you could do is you could draw it like this. You could say, look, there's 1 1/3 to each. So I'm going to draw that with dashes. The dashes, the dots mean 1/3. So 1 1/3, 1 1/3, right? 1 1/3, 1 1/3, 1 oops, 1. Gosh. I'm not used to writing fractions like that. There we go, 1 1/3, right? So this is not an official way to do it. It's just a way that sometimes people will represent it. What we would say is that this particular ion, the nitrate ion, has 3 possible resonance structures, 3 possible Lewis structures, and that the actual structure is the average of all 3. Now, what's the evidence behind that? Well, I talked about energy, right? How much energy it takes to break a bond. So if you measure the strength of a nitrogen-oxygen single bond and a nitrogen-oxygen double bond, they're different. The double bond is stronger than a single. So let's say this one is like 300 and this one's 500. If there was a double bond in there and then 2 singles, you would expect that when you break the bonds, sometimes you'd get 300 and sometimes you would get 500, but that's not what happens. What happens is you get approximately 1 1/3 times the 300, suggesting that yes, in fact, there are no double or single bonds in there. There are averages of single and double bonds. And so the way we determined that was by drawing the Lewis structure, right? We said, look, we have this problem that nitrogen doesn't have enough electrons. So we're going to have to push a pair of electrons over to get that double bond. Well, turns out there were 3 possible ways to do that. And if that's the case, there are going to be 3 different Lewis structures. So we would identify that. Okay. So let me show you an example. There's a couple of different types of problems that, actually there's not. There's actually only one type of problem that the Alex homework has you do. So this is called writing the Lewis structures for a molecule with resonance. Okay, so they say draw the Lewis structure for the polyatomic ion. And so here's an example formate ion. Okay, so they draw it as CHO2 minus. And they say to draw all the possible structures. So draw all possible resonance structures. Okay, well, this one's a little tricky because you have to get the arrangement of the atoms correct. If you recall, last week we talked about how with hydrocarbons, there are particular arrangements of what you see. So this is an example of one of those issues. So here's the way you deal with the formate ion. The formate ion, you have a carbon. So you draw that first. The carbon is the central atom. Carbon is the central atom in organic molecules. When it says CH or CH2 or CH3, that means the hydrogens are attached to the carbon. So there's one hydrogen attached to the carbon. So I'm going to put it over here on the left. You could put it on the top or in the bottom, but we're not going to put it on the right because we have this O2. So when you have carbon with O2, that generally is this: one oxygen and then another oxygen. And again, you could put one on the top instead of the bottom, or one on the top, one on the bottom, or one on the right and one on the top. That's fine, doesn't matter. But those two oxygens are attached to the carbon, okay? So you have CHO2, and be careful, it's not this. It's certainly not this, right? Because hydrogen can only have 2 electrons, and it's not this even. It's not even this. This does exist. If you see that, it'll say it's a peroxide. Peroxides are where you have the oxygens linked together like that, okay? All right, so now that we have the arrangement, 2 oxygens and 1 hydrogen attached to the carbon, now we can just go about our technique. Our technique is we count up the number of valence electrons, subtract the number that we've used, and so forth and so on, okay? So let's take a look. Carbon has 4. Hydrogen has 1. Oxygen has 6, but there's 2 oxygens. And then don't forget this negative. That's an extra. Generally, that negative will give you an even number of electrons. That's why ions tend to exist. That extra electron gives you an even number of electrons. So 4 plus 1 is 5, plus another 1 is 6. Plus 2 times 6 is 12. That's 18. So you got 18 electrons. We've already used 6. So that gives us 12. And remember what we said before? You take them and you divide them up generally equally around the surrounding atoms until they're up to 8. And that just works out perfectly, 12. So we've used all the electrons. I'm going to make sure I have a negative here. And then again, you have this problem, which is the carbon atom does not have 8 electrons. It only has 6. So what you do is you say, okay, how could we get it up to 8? Well, there's an oxygen over here that we could use to push a pair to form a second bond. So that's one possibility. But we have another oxygen. This oxygen could do the same thing. So that's another possibility. So we have 2 possibilities. Remember I said the number of Lewis structures is actually equal to the number of surrounding oxygens, right? So nitrate had 3 possible Lewis structures because it had 3 surrounding oxygens. In the case of the formate ion, it has 2 surrounding oxygens, so it's going to have 2 possible resonance structures. So all we have to do in terms of this problem is just draw those 2 structures, and then we'll be set. We don't have to draw the intermediate, but we do want to understand that it's going to be an average of those 2 structures. There is not going to be this one and this one. It's going to be an average of the 2. Okay. So what do we get? It's kind of like children, right? When you have children, they come about from 2 different people. That child, in a sense, is a statistical average of the 2 parents, right? Ignoring the issue of dominant and recessive genes, but essentially there's a reassortment of your genes, right, of the 2 parents, and you get half of each, right? So it's an average. Same thing here, you get an average. So the first one is where you have the double bond here on the left, and then the hydrogen's not an issue, and then you have a single bond here on the right. Okay, so there's your first one. Second one is you have the double bond over here. So double bond. And then you have this negative here, okay? So there's your 1, and there's your 2, and it's going to be an average of the 2. Usually, Alex is not going to make you do this, but typically when we have resonance forms, we show a double-headed arrow, like I've done down here, to indicate that those are two resonance structures, right? So that tells people immediately, oh, that's the same ions, the same, it's just a different Lewis structure. The electrons are positioned differently. So it's going to be an average of those two structures that we've drawn. Okay, let's take a look at another example. The next one is the polyatomic formyl anion, formyl. So let's try that one. CHO minus. I'm not sure if this one will have any resonance because there's only one surrounding oxygen. So let's see. So again, when you see carbon, that's going to be your central atom. When you see hydrogen, that's surrounding it. And then you see the oxygen, you draw it this way. Okay, CHO. Okay, don't draw it, don't draw it like this, CHO, right? Not possible. Hydrogen is never in the middle. Okay. Okay, we do know it's going to be negative, but let's go ahead and go through our electrons. So carbon is in group 4A. It has 4 electrons, 4 valence. Hydrogen is in group 1A. It has 1. Oxygen is in group 6A. It has 6. And then you got this extra electron. Again, that extra electron is typically what that does is it makes it an even number of electrons so that you can get the octet rule and all of that, right? You can't have an octet rule if you have 7 electrons. You got to have 8 electrons to get the octet. So 5 plus 1 is 6 plus 6 is 12. So we have an even number of electrons. We've already used 4. There's 2 bonds. So that gives us 8. So we put them around the surrounding atom first. So that's 6. But now we got 2 left over, right? 8 minus 6 is 2. Where do we put them? Put them on the carbon. Okay. Now you put them on the central atom. Now we still don't have an octet rule for carbon, right? So what do? We use a lone pair from the oxygen to form a double bond. But there's only one oxygen, so there's only one possible Lewis structure, right? So we're only going to get one. Okay, so it appears, right? But now, this is where we have to get creative. Is there any other way that we could get the carbon up to 8? And I don't know, it's hard to, I don't see any, really. We could, nope, doesn't look like it. Looks like that's it. So it looks like we just have one structure here that's possible, okay? I was gonna suggest there might have been a possibility that we could have a triple bond between the carbon and the oxygen, but that would make matters worse. It wouldn't help. So it looks like there's only one there. Okay. So that's called the formyl anion. And that's the second one. So let's look at another one. I want to show you at least a couple that have more than one Lewis structure. Okay, this is trisulfur. Okay, well, this one might be interesting. This one's a little different. This is not one that has a bunch of oxygens and an anion. So this is called this trisulfur molecule, right? Molecule means it's not charged. It's not an anion or a cation. It's just a molecule, okay? So how do we deal with this? When you have multiple atoms of the same element, typically what you want to do is assume they just form a straight line. Okay, just like that. So same thing, if you saw O3, you would just draw all of them together. There are exceptions to that. So in nature, there are different rings that could get formed, but for many of them, it's just drawn as a straight line, unless you have some evidence that it's something different. And now let's do our bookkeeping, right? Sulfur is in group 6A. So there's 3 times 6 valence electrons. We've already used 4. So we got 14. So what you do is put them on the surrounding atoms first. Get them up to 8. So they're both up to 8 now. You've used 12. You still got 2 to go. So put that on the central atom. Now you've got 14 there, right? You can check. 18. Do we have 18? 2, 4, 6. Right? There's 6. There's another 2, there's another 2, there's another 2, and there's another 6. So 6, 8, 10, 12, 18, got 18 electrons. Okay, that's important. You can't draw Lewis structures and end up with more electrons than you're supposed to have. There we go, 18 electrons, no ions, so we don't need the brackets. Okay, so what's the next step? The next step is to get that central atom up to 8. It only has 6. It has 2 bonds and a lone pair, that's 6. So, but again, take a look at, inspect. You got to look at this. This atom could do it, so that's a possibility. Or this atom could do it. That's another possibility. So there's a couple of possibilities. So let's draw those too. I was going to put, I don't know why, so many of these have oxygen, so I tend to put oxygen. Okay. So we're, this is structure 1 that I'm drawing here. Okay, this is 1. Okay. Still, 18 electrons. Don't create or lose electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay. Double bond to the sulfur on the left. But the second possibility is you have a double bond to the sulfur on the right. Okay. So 2 lone pairs and then 3 lone pairs over here. Okay, so what you're doing is you're using the surrounding atoms to form an extra bond. When the surrounding atom forms an extra bond, if there's more than one of them that are capable of it, then you have 2 possible Lewis structures. Okay, if you had 3, if there were 3 surrounding atoms, then you'd have 3 possibilities. If there were 4, you'd have 4 possibilities. Okay, let's see. Okay, formate. We already did formate. Okay. We already did nitrite. So, most of these we've already done. Here's an SO2. You could do SO2 on your own. Okay. All right. So there's your issue of resonance. So resonance ends up being important in some really famous chemical molecules. So let me show you, one example where it's very important. There is a molecule called C6H6, or that's the formula for it. It's called benzene. And the reason benzene it's important for various reasons, but one reason it's important is that it appears a lot, derivatives of it appear a lot in nature, and a lot of biological molecules possess it. So for example, there are these amino acids called phenylalanine and tyrosine. They are essentially based on their derivatives of benzene. And so it's a very common and important type of structure. Benzene is actually an example of a ring. And this appears in nature. It was a pretty famous chemist figured it out, that it was a ring. And so what happens is you have 6 carbon atoms in the, geometrically it's a hexagon. C6H6, okay? And then what happens is you get 2 possible structures. So here's 1, okay? Where you have a double bond, a single, a double, a single, a double, a single. So we call that alternating double bonds, meaning that each carbon atom has 1 double bond, but not all the bonds are double. It's like double, single, double, single, double, single, alternating double bonds. But it turns out that that's only one possible structure. The other possible structure is that the double bonds are displaced, meaning that they move 60 degrees. No, I made a little mistake here. So double. Yeah, okay, so let me draw these hydrogens. I kind of drew this at the bottom. Sorry, so I have to do it that way. So I'm sorry, I see what my mistake is. There we go. So this is the second one. So this is number 2. Okay. So the only difference between 1 and 2 is where the double bonds are. Instead of being instead of starting here at the top, let's count them. 1, 2, 3, 4. Those are the carbon atoms, 5 and 6. Instead of the double bond being between 1 and 2, 3 and 4, and then 5 and 6, the double bond here is between 2 and 3, 4 and 5, and then 6 and 1, right? So it's been pushed over. Those are the two structures. So what happens? It's actually the average of the two. So how do we draw that? Well, we can use a notation that's really cool. Instead of actually drawing the symbols of the carbons, we just use geometric figures. So when we use a hexagon, okay, that's my crude attempt at drawing a hexagon, the points are the carbon atoms. So there's 6 carbon atoms. And then we don't even draw the hydrogens in. We ignore the hydrogens, okay? They're in there. They're implied that they're in there, but we don't draw them. And then we draw the single double bonds. So in the first structure, we had this way, right? See how kind of clean that is now? It's a lot cleaner than this is over here. It's a lot simpler. It's just a little geometric figure so you can see the structure. Same thing down here. This second structure, okay, again, 1, 2, 3, 4, 5, 6. Now the double bonds are here. So this notation allows you to kind of see more clearly where the double bonds are and where the single bonds are without having all the symbols of the elements in there. So what happens? It's an average of the two. So how do we represent that? Typically, the way it's represented, again, this is resonance. So you have these two different structures. It's an average, right? So the way this is usually done is to say that these electrons in the double bonds are delocalized around the carbon atoms in the form of a ring. So we just draw a little circle in the middle. And that circle, although you don't know how many electrons that's in that circle, there are rules you can use to figure them out quite quickly, right? So we're losing the information about the symbols, but we know that those points on the hexagon, you know, those vertices, they are carbon atoms, and we know they're attached to hydrogen atoms. And when we draw it like this, so this right here is your average. That's your average of 1 and 2. Right? The average of 1 and 2. Okay? So there are many molecules and many ions that are found in nature that exhibit this phenomenon called resonance. And although we won't go into it in this course, if you go on to take more advanced chemistry courses like organic chemistry or biochemistry or cell biology, you will start to talk about molecular biology. You'll start to talk about how resonance has the ability to make certain molecules more stable than others and make it harder to break bonds compared to other molecules. Okay, so it's not a surprise that it exists in nature. It's not a surprise that it exists in biochemistry because it does lend itself to certain types of stabilities. Okay, so that's resonance. Let's talk now. I'm going to move on to the section called 8, or it's 8.8. It's called exceptions to the octet rule. Okay. And with exceptions to the octet rule, we're going to focus, let me just make sure. We're going to focus primarily on what's called expanded octet. I don't think we're going to look at electron deficiency. Yeah, let's just do expanded octet. Okay, so here's the issue. So far, we've talked all about this octet rule, right? This magical octet rule. And what we said was, essentially what happens is, when you look at the electron configurations of the elements, the nonmetals, you know, so this is your second shell, right? Shell 2. You've got this number of orbitals, right? So you have an orbital here for the 2s, and then you got 3 orbitals for the 2p, right? That's going back to chapter 6. That's 4 orbitals in that shell. Each orbital can have 2 electrons according to the Pauli exclusion principle. So that's 8 electrons, right? So that's the octet rule, right? Essentially, there's room for 8 electrons. So once you get up to 8 electrons, there's a quantum mechanical stability that exists with 8 electrons, right? What happens, though, when you get up to the 3rd shell? Let's think about that for a moment. When you get to the 3rd shell, you have something different happens. You now have 3 Ds, right? So there's no 8 electrons here. It's actually 18, right? It's actually 18 electrons. 2 here, 6 here, and 10 here. 2, 6, 10, right? That's the maximum number of electrons. So you get a maximum number of 18. In fact, there is in chemistry something called the rule of 18, right? There's the Duet Rule for hydrogen, 2. There's the Octet Rule for carbon, nitrogen, oxygen, that's 8. And then there's the rule of 18, which is for the elements that are further down the table. So really what we're seeing here is that if you look at row 1, hydrogen and helium, it's the Duet Rule. And the reason it's the Duet Rule is because there's only 1 orbital in the first shell, the 1s, and it can only handle 2 electrons. So Duet Rule makes sense. And then you get to the 2nd row, and here's where you have lithium and beryllium and boron and carbon and nitrogen and oxygen and fluorine, and then neon. Here we're in the 2nd shell, Octet Rule. But again, it's because it's 2s, 2p. That gives you 8 electrons maximum. That's why we have octet. But when we get to the 3rd row, and that's where you have sodium and magnesium and aluminum and silicon and phosphorus and sulfur and chlorine and argon. Well, now it's really the 18 electron rule, which is 3s, 3p, 3d. But we're not going to have you worry about the 18 electron rule. That's something that chemists worry about. It's something you would do if you were taking an inorganic chemistry, looking at metals like iron and metals like cobalt, that sort of thing. Nickel, we're not going to worry about that for here. But the point is that when you get to the 3rd row and beyond, there is more than 8 electrons possible. And so what I'm going to do is I'm going to show you this idea of what we call expanded octet. Expanded octet means greater than 8 electrons in the valence shell of the central atom. And I'm going to underline central atom because that's a key to you being able to do the problems. The central atom is what we're talking about here. Only the central atom, not the surrounding atoms. What is observed is that surrounding atoms universally obey the octet rule. Okay, I'm not going to say it's 100%, but they generally obey the octet rule. But the central atom can disobey the octet rule. And so how do you know? What you do is you first identify the arrangement of atoms. So if you have an arrangement of atoms where the central atom is in the 3rd through the 5th rows, then this idea of expanded octet is possible. It's not guaranteed. The central atom may obey the octet rule. It may, but it has the potential to disobey the octet rule. And so if it does, what you do is you use formal charge to evaluate. If the central atom is expanded, then the formal charge will equal 0 for that atom. Okay, so in other words, if you're trying to figure out whether the best Lewis structure is expanded octet for the central atom, just use a formal charge calculation. If you come up with a Lewis structure with an expanded octet, and then you do a formal charge calculation, you get 0 for that central atom, that means you got the correct structure. If you end up with an octet rule and you do a formal charge calculation and you don't get 0, that means you need to then convert it to expanded octet. So let me show you an example. I'm going to begin with SF4. Let's do SF4. That's what it looks like. So we're going to draw the Lewis structure for SF4. Okay. So let's see. You're going to do it pretty much the way you did it before. You identify the central atom. So here's sulfur. You've got 4 surrounding atoms. Count up your valence electrons. Sulfur has 6. It's in group 6A. Fluorine has 7. It's in group 7A. But there's 4 of them, so that's 28. So 28 plus 6, right, is 34. This is not an ion. It's not SF4 plus or SF4 minus. It's just SF4. So it looks like we got 34 electrons, right? Okay. Often 32 is common, but this one has 34. Okay. So next step. We've already used 8. You have to have 1 bond at least. So that's 8 right there. So minus 8. So now you've got, what is it? 34 minus 8 is 26. So let's do what we normally do. We get the surrounding atoms up to 8 by putting 3 lone pairs. So what has happened? We've now used 24, right? 6, 6, 6, 6 is 24. We got 2 left. Can't put them on the surrounding atoms, so we put them on the central atom, just like we've done before. Now there's no... You can put them at the top, you could put them at the bottom, but you just got to have them in between those bonds, okay? So now here's the issue. Look at that sulfur, that central atom. It has more than 8 electrons. That's what we would call expanded octet. Let's justify it. First, here's your test. Is the central atom in the 3rd to 5th rows? Okay, well, sulfur is. Sulfur is in the 3rd period of the periodic table. You know, it's oxygen's in the 2nd period, sulfur is right beneath it, it's in the 3rd period. So that's your first test. So yes, so that means it could have expanded octet. 2, is the formal charge equal to 0? Let's test that. We did that yesterday. Here's our little review of formal charge, right? We're just going to do it for the sulfur, okay? Sulfur has 6 valence electrons. We subtract the lone pair, and we subtract the number of bonds. And that's 0. Hey, look, the formal charge of sulfur is 0. If that's true, if it's in this, if the central atom is 3rd to 5th row, and then expanded octet gives it a formal charge of 0, you pretty much got it. It's got to be right. If we'd ended up with a formal charge of -1, then we would have a problem. But it came out to 0, so that means it's pretty good. Okay. There was really no other choice. Where else were you going to put the electrons? You can't put them on the fluorine because the fluorine is in the 2nd row. It never violates 8. It never has 10 or 12. So it has to go on the sulfur, and the formal charge worked out to be 0. Okay, let me try another one. PF5. Okay. Now I can give you a little hint on this one. This one has to be expanded octet if you think about it. It has 5 surrounding atoms. It's got to have at least 1 bond to each surrounding atom. So that's 2 times 5. That's 10 right there. That right there tells you it's got to be expanded octet. But let's justify it. I'm going to draw the Lewis structure. Now we got 5. When you have 5, you can kind of sort of draw it like this. You can't draw it as a box anymore because you got 5. So just draw it like a little star or a little pentagon if you want to think of it that way. Okay, let's count up our electrons. Phosphorus is in group 5A. Okay, now we're doing 3rd row, so you may not be as familiar with these elements. You would know that nitrogen is in group 5A, but phosphorus is right beneath nitrogen, so that's 5. And then fluorine is in the second row. That's group 7A. So 5. There's 5 fluorines. So 5 times 7. That's 40. A lot of electrons, right? Once you start getting to fluorine has a lot of valence electrons. Fluorine, chlorine, and bromine. So you have a lot of lone pairs. Okay. So we've already used 10, right? 5 bonds. So that's 30. Just divide each fluorine by 6, right? You got 30 electrons, so you put 6. You're going to put 3 lone pairs on it because it's got to get up to 8. And then what's going to happen is it's actually going to work out perfectly. By putting 3 lone pairs, putting 6 electrons around each fluorine, 6 times 5 is 30. That's exactly what we have here. Okay? But let's justify this now. We have an expanded octet clearly. There's 10 electrons around the phosphorus. How do we deal with this? You do a formal charge calculation, and then you identify what row it's in. Phosphorus is in row 3. So definitely if it's a central atom and it's in row 3, remember it's 3, 4, or 5, right? Any of those rows, 3, 4, or 5. So arsenic below it is in the 4th row. That would work as well. If it's in the 3rd, 4th, or 5th row, it has the capacity for expanded octet. So then you do your formal charge. Okay, you take the number of valence electrons for phosphorus, 5, and you subtract the number, we called it associated electrons yesterday, right? The associated electrons, a lone pair counts as 2, a single bond counts as 1, a double bond counts as 2, and a triple bond counts as 3. Well, there's a lone pair, so that's, I'm sorry, there's no lone pairs. My apologies. There's no lone pairs on the phosphorus, right? But there are 5 bonds. And so 5 minus 5 is 0. So the formal charge of phosphorus is 0. And that was our second test. Central atom needs to be in the 3rd, 4th, or 5th row. Phosphorus is. And then your formal charge should be 0. Okay, it is. It's a formal charge of 0. That right there justifies this expanded octet. Okay, let's see. I've got time for one more. Here's an interesting one. Let me see. Actually, I'm gonna want to see if there's one. Okay. I was hoping they would actually maybe give you one that had a. Oh, here it is. XCF4. Oops. Okay, so let me show you one more. This one can be a little tricky here. So look at this molecule. I was searching for it. I was thinking they might give you one like this, and they do. Okay, so XCF4. Okay, what you may notice about that one is xenon is a noble gas. And noble gases, we typically say, are unreactive. You don't form molecules. They're elements, right? It turns out that back in the 1970s and 80s, these very motivated chemists wanted to see if they could force noble gases to form compounds. And they succeeded by using highly electronegative elements like fluorine and oxygen. Those are the most electronegative elements. The logic was that fluorine is so electronegative that the reason xenon would not form a molecule is it already has 8 electrons around. It's already full. So it doesn't need any more electrons to get up to 8. So if it was going to form bonds, it would have more than 8. So how could that happen? Well, if you take something that's highly electronegative like fluorine, it's going to pull away so much of those electrons toward itself that it might kind of reduce the total number back down to 8 for xenon, and you would be able to form a compound. And it turns out it worked under extreme conditions. Now, they aren't very stable. They break down over time, but they were able to make compounds with xenon, compounds with krypton. I don't think argon, maybe argon, but I haven't seen any compounds with argon, and definitely not with neon, but with the lower 5th and 6th rows, they were able to do it. Okay, so here's how you approach this one. Xenon is going to be the central atom, and it's got 4 surrounding atoms. 1, 2, 3, and 4. Okay, now let's do our electrons. Xenon is in group 8A, right? Xenon. So here's group 8A. You've got neon, argon, krypton, xenon, and radon. So those have 8 valence electrons. So you got 8. And then in group 7A is fluorine, right? So you've got 4 times 7. 36. That's 36 valence electrons. We've already used 8. So you have 28. So what do? Same thing we talked about before. You put 3 lone pairs on all the central atoms until you run out of electrons. And if you have any left over, you put them on the central atom. Okay, that's 24. 6, 12, 18, 24. 4 remaining. Where do you put them? You put them on the central atom. Typically, you put them on opposite sides like this. Okay. Okay, well, xenon is definitely 3rd, 4th, or 5th row, right? It's actually 5th row. And arguably, radon could probably do the same thing. I think they have made compounds with radon as well. That's in the 6th row, right? 3, 4, 5, 6, 6 rows. So it probably actually acts in the 6th row as well. So it's, that's our first test. Is the central atom 3rd, 4th, 5th row, or 6th row for that matter? Xenon is. Second test, formal charge. Are you going to get a 0 formal charge? Let's see. So the formal charge for xenon would be you take the number of valence electrons, which is 8, and then you subtract the number of associated electrons. Now there's 2 lone pairs, so that's 4, and 4 bonds, so that's 4. It works out perfectly. 8 minus 8 is 0. Okay, so it does have a formal charge of 0. So that means that our Lewis structure is a pretty reasonable one. Okay, and this would be an accepted Lewis structure for xenon, tetrafluoride. Okay, so there you go. That's section 8.8, which is exceptions to the octet rule. And we really just have one more topic, which is bond enthalpy. That's 8.9. So we'll look at that tomorrow, which is Thursday, and that will wrap up this chapter. We'll be done with chapter 8. And then next week, what I'm going to do is I'm going to go ahead and start working on your extra credit assignment. Your extra credit assignment on Alex is the homework, the objective for chapter 9, which is called Chemical Bonding 2. So we're going to look at, it's just 8 topics that we have in there. So I'll start working on that on Tuesday. And, there's only 8 topics, but you get just as much credit for that one as you get for the other chapters. So it's worth your time to do it. If you are going to go on and take more advanced chemistry, I do recommend, even though it's extra credit, I do recommend you doing chapter 9, because those, it's more practice at doing Lewis structures, and we're going to discuss hybridization a little bit. And those are important topics when you get to organic chemistry. You will cover it in organic chemistry, but it's always good to have kind of an intro to it, a little introduction, so that it doesn't seem so mysterious to you when you start that new course. Okay, so we'll do that next week. But tomorrow we will finish with bond enthalpy, and that will wrap up this chapter. This chapter is not due until June 6th, so you still have quite a bit of time to do it. In fact, chapter 6 is not even due yet. That's due on the 23rd. So if you're still working on chapter 6, which many of you are, of course, you can still go back and watch the old videos from chapter 6 and then get up to speed on chapter 8 later on. There's a lot of topics in chapter 8. It's 18 topics. It's a big one, but you still have until June 6th to finish that up. Okay. So have a great day. I will try to upload this. It may take me a little bit later. It might be up. Well, actually, no, I'm going to try to upload it now. So it should be up within an hour or so. You'll have it today. Okay. Have a great day.
Thank you.